All right, welcome. How are you doing today? My name is Guy Royce, and this is Probabilistic Data Structures. Um, I hope you're having a good time today. Yesterday was the big day with all the talks. Today is the big day with all the training sessions, and probabilistic data structures are a particularly interesting one. So let's proceed, shall we? This is just slides talks about me. Basically, just says that I've written a lot of software, and I like to share what I know. And I work at Redis Labs as a developer advocate. So if you want to check that out, you want to check me out, go ahead, check me out on social media. I always like getting more Twitter followers. Don't mind that at all. But go ahead and check me out. But that's really not why we're here today. We're here today to talk about probabilistic data structures. And if you're anything like me, when I joined Redis, I had never heard of probabilistic data structures. It just wasn't something I had encountered. And so we've got a big agenda to talk about the types that we have, the types of probabilistic data structures we have within Redis. We're going to talk about what they are. We're going to talk about Redis and Redis Bloom. We're going to talk about particular ones. There's 5 specific ones we're going to talk about. We're going to talk about HyperLogLog, which is used for computing cardinality, which is to count things in a set. We're going to do Bloom and Cuckoo filters, and those are both used to measure membership, to check to see if a thing exists within a set or not. We're going to talk about count min sketch, and count min sketch helps you determine the frequency and find the frequency of items in a set. And we'll finish it up with top K, which will reveal the rank of items within your set. And so with that alliterative agenda done, let's move on to probably the most important thing is, what is a probabilistic data structure? Well, a lot of people, as it turns out, have this question. I did an informal survey on Twitter and asked everyone, quick developer survey, have you heard of probabilistic data structures? 58%, by far the majority here, have never heard of them. 22% had heard the term before, and that was it. I'm tempted to believe that some of them may have heard the term in this very survey, because sometimes developers can be a bit, shall we say, literal-minded. But, maybe not. But that if you take those two together, that's a solid 80% of the respondents. Now, this is not very scientific, right? It's 119 people voted on a little Twitter survey, but that's 4 out of 5 people have never heard of them, or have only heard of them but have never done anything with them. They didn't really know what they were. We're sort of into trident dentist ratios at this point. 9% knew what they were, and 11% had actually used them. And so about 20% of developers know what they are or have used them. Odds are you're in the 80% category, and so you're probably wondering what they are and how to use them, which is why you're here. So I'm going to help elucidate you today and explain what they are and show you how you can use Redis to use them. To understand probabilistic data structures, I think it's worthwhile to think about deterministic data structures. There's probabilistic, and so there's got to be some sort of opposite that we can use as a way of describing this. And a deterministic data structure is, well, it's the data structures you know and love and use already. If you're a Java developer, you've used lists, and we call them tables, the hash tables, but in Java they're maps and hash maps. You got the sets, you got arrays, you've got graphs, tuples, stacks, trees, tables, queues. If you've taken computer science, you've probably had to build these in C++ at some point in your career or in your education. I actually started out fairly early in my career doing a lot of C++, and we had to, there weren't shared libraries like there are today, and so we had to, every time I got on a project, we had to create our own linked lists and sets and hash tables and that sort of stuff. But the thing with deterministic data structures is that, well, they're deterministic. You give them a thing, and you get it back, and you give it a thing again, and you get it back again, and it's consistent. You consistently get these things back. They always do what you expect them to do. They're always truthful. And that's what makes them deterministic, as opposed to probabilistic, which doesn't necessarily do that. Now, we pick our different deterministic data structures based on time and space complexity. So we might be looking at, something that's very efficient time-wise, so it's fast, but it consumes more space. Or maybe we're looking at something that's a more compressed space, but is slower to use. And so we make these trade-offs all the time between time and space. Do we want to have an array list or a linked list, which is fairly space efficient, but if you want to find anything in it, you got to walk the entire linked list until you find the thing you're looking for. So it makes finding things kind of slow. Or do you want to use something like a hash table where finding things is constant? You can use the hash and find the point in that hash table immediately, but it has some empty space in it. And so it's not using that space as efficiently as it could. And so we make these trade-offs all the time. But actually, we don't always make them between time and space. We also make them within time and space. So some operations for a linked list are fast compared to that of, say, an array, whereas other operations on an array are fast compared to that on a linked list. And so we're even making just time trade-offs depending on the types of operations we have available. And so they're not even really in opposition to each other. They're just two complexities that we have to deal with, and we pick them based on our requirements. But there's actually a third thing that you can play with, and that's accuracy. Can we save time and or save space in this data structure if sometimes it's wrong? And you're probably thinking, why would I want a data structure to lie to me? Well, if you don't want a data structure to lie to you, use a deterministic one. However, sometimes the scale of your data is such that a little bit of inaccuracy is worth it. And you've made this trade-off yourself, probably without really thinking about it too much, with JPEGs. So here's a beautiful picture of the Devil's Tower, made famous by that wonderful film Close Encounters of the Third Kind. I feel like this picture means something. That joke's for the people that are all over 40. Thank you for laughing at it. But in this image right here, right, we've got this little section of blue sky here. Now, odds are, as a JPEG, that little section of blue sky is the wrong color. Like some of those pixels are wrong. But you can't see it because it doesn't matter. And so this has inaccuracy in it. In a way, you could kind of think of a JPEG as a probabilistic data structure. It lost some of the data when it was put together. And when you pull it back out, some of that data is lost, but you don't notice it because it blends in with the background. It's an acceptable level of error to get the space savings, to reduce your space complexity. And so I like to think of probabilistic data structures in the same way. They're a little bit lossy, but good enough. And lots of times that's a great trade-off to make. The probabilistic data structures in Redis Bloom are all variations on a set. So a set is your classic, container or collection of unique items, unique members. Here we've got a set represented with some curly braces and some completely arbitrary shapes that I totally picked at random and aren't in our logo at all. So this is a set of 4 shapes: a star, a square, a circle, a triangle. Normally with a set, you can add, remove, and get the members of it. So I can add another shape. I can remove a shape. I can get all of the shapes that are in it. I could take the set and union it with another set, or intersect it, or do difference operations and find out what's different between the two sets or what they have in common, or just make a superset of them all. I can check for membership. I can say, is that square in the set? And I can get the cardinality of the set. I can say how many items are in the set. And all of the probabilistic data structures are kind of like that, but they have subsets of the operations available. So you might not be able to remove things, or you might not be able to get things, but you can add things. Or you can add things, but only if they're a certain type of thing. Or you can get things, but only if it's in a certain class. And so they have special properties that make them unique. And sometimes you can't do them at all. Most of the probabilistic data structures we're going to look at today are part of Redis Bloom, which is a module. The exception is HyperLogLog. That ships standard as part of Redis. Redis Bloom is a module. It's an extension, a plugin that expands the capabilities of Redis. And in it, we have 4 data structures: Bloom filters, Cuckoo filters, Count Min Sketch, and Top K. And we have lots and lots of modules. These little icons down here are some of the different modules we have. The one on the far right here, that is the one for Redis Bloom. Graph, AI, search, time series, JSON, and gears. And there should be training on many of these available, so hopefully you check some of them out. Lots of them are very interesting. So, Redis Bloom's the module. It's providing these probabilistic data structures. Let's start diving into what some of them are in greater detail. Let's take a look at HyperLogLog first and count cardinality. So what the heck's cardinality? Well, cardinality is the number of members of a set. It's actually a pretty simple idea. Hey, we got 4 things in this set. That's the cardinality. It's just counting. And so here we have a star, a square, a circle, and a triangle. There are 4 shapes in this set. You could add a square to the set again, but there would still only be 4 unique shapes in this set. And so the cardinality would still be 4. And that's all cardinality is. HyperLogLog is really good at counting cardinality. HyperLogLog sets support adding members, so you can always add to that set. All these generally allow you to add things. If you can't add things to a set, it's kind of useless. It allows you to count the members, which is the cardinality. It's the point of HyperLogLog. And it can actually participate in unions, and so you can take a couple of HyperLogLogs and join them together to create an uber HyperLogLog. It does not support getting the members, so once you shove them in there, you can't get them out. You don't know what they are. And you can't delete the members. You can't remove them once you've added them. And of course, it doesn't support intersections or differences either. But you can add, you can count, and you can combine. And that's actually a pretty good capability. Adding a new item and getting the cardinality is an O of 1 operation. So constant time just takes the same amount of time no matter how big it is. If you are going to do a union, if you're going to merge multiple HyperLogLogs together, it's O of n. So n being the number of things you want to merge. So if you've got 3 HyperLogLogs, you want to merge them together, then it's going to take, that many. It's O of n for 3. I think this is really cool. Each HyperLogLog will occupy at most 12 kilobytes. 12 kilobytes. That is nothing. It will never occupy, no matter how much you add to it, will never occupy more than 12 kilobytes. Now, I'm recording this video on a MacBook Pro, and I've got 16 gigs of RAM. That is 6 orders of magnitude more than a HyperLogLog will take at its maximum. You're not going to... The amount of space is just trivial. It would fit on an old school floppy disk. Even the big, 8-inch ones. And the error rate of the cardinality is at maximum 0.81%. So that's not a very big error rate. It's less than 1% of an error rate. So the performance of HyperLogLog is actually rather impressive. If you want to use a HyperLogLog in Redis, there are 3 commands. pfadd, which adds elements, surprisingly. pfcount, which you can hand it a key, and it will tell you what the count is of that particular HyperLogLog, or HyperLogLogs. And pfmerge. pfmerge will allow you to take multiple HyperLogLogs and merge them into a single larger HyperLogLog. Well, not larger, it's still only 12 kilobytes, but with more stuff in it. You might be wondering why these all start with PF. PF is the initials of the man who invented this particular data structure. His name is, and I'm going to try not to butcher this, it's in French. And regrettably, I don't speak French, but it's Philippe Flageolet. Yeah, Flageolet. And so we put those initials there as a way to sort of honor his contribution to, humanity, I suppose. So that's what the PF is there for. Why would you use a HyperLogLog? Well, and this is going to be something we say a lot when we're talking about probabilistic data structures. You would use it when you're trying to count things with a small footprint, or when you're trying to rank things with a small footprint. It's always with a small footprint. Things that you might want to count is unique views of a video. Say you're a large video hosting service, which we all use all the time, and you want to say how many unique views there are, you could create a HyperLogLog for that video. And in that HyperLogLog, you would add, for each user, you would add the users to that HyperLogLog. That way, if I went and really liked a particular YouTube video and watched it 12 times, it would only increase it by 1. Or if I was a person creating YouTube content and was trying to up my scores, I couldn't game the system that way. Same idea for upvotes, likes, and hearts on posts on social media. You could use this to track unique visitors to a website that you're running, maybe based on IP address. You could look for unique search terms on a search engine. How many unique, distinct things have people searched for? Well, I'm sure there are many other uses that you can think of. You probably have some that you're thinking of right now. A HyperLogLog actually can count a virtually unlimited amount of unique items. And this actually kind of surprised me because it's 12 kilobytes and you're adding a lot of stuff. And the things you add, the size of them doesn't matter. It could be documents that you're adding here, or it could just be words. But you can count a virtually unlimited number of unique items. When I heard about this, I asked the person that told me, and he told me that it will break down eventually, but it's in the number of atoms in the universe sort of range. So we're probably not going to run into that limit anytime soon. And so you can store a lot of stuff in there. And there's actually one other significant use case, which is if you're Reddit. Reddit uses HyperLogLogs to count views on posts on Reddit, and they have a little blog post here that they wrote about it a couple years ago. It's worth checking out. It's a great use case. Adding to a HyperLogLog is very, very simple. Just call pfadd. The HyperLogLog will be instantiated, will be created by just adding something to it. And you give it a key, and you give it an item to add. Here we're adding an IP address 10.0.0.23. Call pfadd again, pass in multiple items. We're going to add 2 more IP addresses. And so this is tracking, say, visitors to RedisConf's website on yesterday, actually. And we'll add another IP address, and we'll add 1 more. And you'll notice that each time we've done this, this returns a 1. But this last time, it returned a 0. And the reason it did that is because we've used this IP address here before. And so this particular command, this particular call to pfadd, did not change the state of the HyperLogLog. Since it didn't change the state, it returns a 0 to say that that has not been changed. And so we should have 4 items if we were to go call pfcount. So let's do that. Here's all our adds. We call pfcount, and it returns 4. So it's your turn to try this out. Go ahead and get your Redis environment set up from Redis CLI. And we got a little exercise here. It should take you about 5 minutes. When I'm done yakking, you can pause the video, work through the exercise. And take as much time as you need. It's a video. You can pause me, right? And create a HyperLogLog named Marvel. And in there, put 3 of your favorite Marvel superheroes in there. We got a couple there listed: Iron Man, Spider-Man, Thor. All the classics. And go ahead and then count it. And then do the same thing for some DC superheroes: Superman, Batman, Aquaman. And check the count of that as well. And so you have 3 of each of these. You should see 3 coming back. Call count on both of them and see what you get back. And then what happens if you cross-contaminate your universes? What if you add Superman to the Marvel key? What happens when you call pfcount against Marvel, against DC, and against both of them? Go ahead and try that and find out how that works. And I'll be here when you get back. Okay, so hopefully that was a fairly painless exercise. And you found that when you call pfcount and merge those things together, that it does indeed merge them, and Superman doesn't get counted twice. But if you count them separately, Superman would get counted twice if he was added to both universes. You can actually merge HyperLog logs themselves with the pf merge command, and you give it a key you want the new content to go into, and the keys of the source content. So here we've done several adds to add IP addresses for today, for the training day, for RedisConf. And then we're going to merge them together into a total visitor count based on IP address for all of RedisConf. And when we've done that, we can call pf count, and that will give us the unique count of all of that. Now we could have also called pf count with the two source keys and gotten the same number, but now we have a new data structure that's merged them together, and we could remove the previous one. This is a way that you can sort of collapse down and save space, so that if that 24 kilobytes is too much, you can collapse it down to 12 kilobytes. Interesting thing about HyperLogLog is it's actually stored as a string. So you can get it, and you'll get this string, which it's the binary representation of that HyperLogLog. I'm told that you can take the string and then set it, and then use HyperLogLog on it again, but I've never tried it, and I don't recommend it. It might be fun to play with if you get a little bit of spare time, see what happens. My advice is just don't mess with this. But it's interesting that it's stored as a string. And in fact, you can even call string length and get the length of that string. Okay, so next we're going to look at Bloom and Cuckoo filters. And I've lumped these together because they're both about checking membership. So what is membership? A member is any one of the distinct objects that make up a set. Yeah, I just read the slide to you. A member, but that is what they are. They're one of the objects in the set. The square is a member of this set. The triangle is a member of this set. And you can check the membership of a set by saying, is the square in here? And it will return true or false. If we ask for a square, it's going to return true. If we say, is there a pentagon? And then that's going to return false because there's no pentagon in this set. Bloom and Cuckoo filters represent this sort of set. A Bloom filter supports adding members and checking membership, and nothing else. You can't get the members, you can't delete the members, you can't do unions, intersections, and differences, you can't count the members. All you can say is add, and is it in there? Cuckoo filter is almost the same, except it also allows you to delete things. And so once you've added a thing, you can also remove it. Bloom and Cuckoo filters are fairly comparable. They solve very similar problems. And so you might be asking yourself, well, I don't need to delete, so why should I pick one over the other? Well, if you find yourself in that scenario, this is your answer. Bloom filters perform better when adding members, whereas Cuckoo filters perform better when checking membership. So if you have to add a lot but you don't check very often, use a Bloom filter. If you have to check a lot but you don't add very often, use a Cuckoo filter. They both have interesting behaviors when they start getting full, when they start hitting their capacity. With a Bloom filter, if you add too many things to them, they can start degrading their accuracy. And they can get to the point where they always just say, yes, it's in there, even when it's not. A Cuckoo filter, when it gets full, can say, you can't add anything else to me. We're full, we're done, we're closed. And so this is kind of interesting. Also worth noting is Bloom and Cuckoo filters can return false positives, but they never return false negatives. So what this means is that if I ask a Bloom filter, is this thing in the filter? Or if I ask a Cuckoo filter, is the square in the filter? It will either say, no, it is definitely not in the filter, or it will say, yes, it's probably in the filter, but you can't know for certain that it's in the filter. You can only return probably and no. Why would you use a Bloom or a Cuckoo filter? My favorite example is unique usernames on a large site. If you're, say, Facebook or World of Warcraft, and you need to check for unique usernames, and you've got millions and millions of users, you can't just scan through all your usernames and pick one and say, yep, that one's taken. But what you can do is you can ask you can load a Bloom filter or a Cuckoo filter up with all of those users. And then you can ask the Bloom filter or Cuckoo filter, which is much smaller and faster, Is this username taken? It will say no, and if it says no, you can believe it, and that user can be created. If it says probably, then you can just say that that's taken and not allow that username to be used. You can determine if a website has been visited before or not by taking the URL and adding it to a Bloom or Cuckoo filter, and then asking, have I been to this site before? You can actually shove entire documents into these filters and check for duplicate content. Have I seen this content before? And you can even have Bloom and Cuckoo filters full of words that you don't want on your site, so that you can filter them out and tag content that has undesirable words, and lots of other uses. Bloom filters are sized using this complex math formula on the right here. The key thing here is that the memory is in bits and your false positive rate. Bloom filters use a series of hashes that it uses to store values in this bit array. And so you can use this formula to determine how wide that bit array needs to be, how many hashes I need to use, and all that kind of stuff. Now, it's math, and it's a little complicated, but it's solvable, but you really don't need to with Redis because it just does it for you. In Redis, you can just create it and say, make it hold this many items, and this is my acceptable error rate. Some examples of how much space is stored. If you want to put 1 million items, size doesn't matter the item, it's just the quantity of the item. With a 1% error rate, that's a little over a megabyte. If you want to drop that all the way to a tenth of 1%, that's 1.7 megabytes. And if you want to take it all the way down to a 100th, or is it a thousandth of 1%, it's 2.8 megabytes. And so that's 1 million items crammed into a fairly small number. Don't exceed the capacity. I mentioned this earlier. As the Bloom filter fills up, it will just say everything's in it. However, if you're using Redis Bloom, that won't happen because, as we can see here, it will just automatically add another filter for you, which is a great feature. However, it does degrade the performance because now it's got to check 2 filters instead of 1, and so it slows it down. Using Bloom filter, you've got the BF reserve, BF add, BF mad, BF exists, and BF exists. Reserve sets up your Bloom filter. You give it a key name, you give it an acceptable error rate, and a capacity. I want it to be right 99% of the time, and I want my capacity to be 10,000 items. To add things, you just call add. If you want to add multiple things, you call multiple add. If you want to check to see if something exists or multiple things exist, you use the exists commands, and they're really straightforward. Setting up a Bloom filter here, we've got an error rate. Here we've decided that we want 99.5% of them to be correct and only 0.5% to be incorrect. And so we put in 0.005 and a capacity of 100. And we're going to create a username store. And we're going to add some users. Here we've got, we're adding T. Edison, and it returns a 1. Here we add G. Westinghouse, also returning a 1. I think they're playing a game called Power Grid. And then here we've added multiples. Here we added N. Tesla and T. Edison. And you'll notice this time we get a 1 and a 0 back. And that's because Nikola Tesla was not in the Bloom filter, but Edison already was. And so it returns a 0 to say that we didn't change the state of the Bloom filter. To call exist, you just say exist, key, and the item. Here T. Edison exists. Here G. Westinghouse exists. Here we're using M exists, and of course Tesla and Edison are both in this filter. So this is your chance to play around with Bloom filters. Go ahead and set up a Bloom filter to contain fruits that you've eaten, or maybe fruits you want to eat. I personally have never had dragon fruit. I hear it's good. Give it a name of fruit, a capacity of 100, and an error rate of 0.5%. And then check that your filter's empty and say, hey, these fruits aren't in there. Add some fruit. Check that fruit check that fruit you have added are probably in the filter. You can't know for sure, but you can, with 99.5% accuracy know that they are. Check that fruits you haven't added are definitely not in the filter. And so if you haven't added banana, you check for banana, and it's not there, it's not there. Go ahead and set up, when you're done doing that, set up a ridiculously tiny Bloom filter. We're going to try and make it error. Give it a capacity of 2 and an error rate of 75%. Add a bunch of fruit and see if you can start getting fruits that you didn't add to be returned by the bloom filter. And this is so you can sort of experience what happens when they're overly full. So with a capacity of 2, you could probably add 5 or 6 fruits and start seeing this behavior. And so go ahead and pause the video and work on this exercise, and then we'll be back in just a moment. All right, so hopefully that was a fun exercise, and bloom filters are a little less intimidating. They're pretty straightforward to use. Let's work on. Let's crack on and get into cuckoo filters. We've talked about cuckoo filters and bloom filters in contrast, and I've shown you the details of bloom filters, but let's go into the cuckoo filters themselves. Cuckoo filters actually can count items in addition to checking for membership. These counts are probabilistic and they're not terribly accurate, so this isn't its primary purpose, but it is a thing that you can access. You can add items more than once, and as you add them multiple times, the count goes up. You can also delete items, and as you delete them more than once, the count goes down. The false positive rate is not under your control. It's just a feature of how cuckoo filters work, and it depends on how full it is, but it's usually about 3%. Big caveat, don't delete items not in the filter. Bad stuff happens. If you delete something that's not in the filter, some other value might be decreased instead, and you'll start getting false negatives, which aren't supposed to happen with bloom and cuckoo filters. But if you delete stuff that's not there, that will happen. If you add beyond capacity, cuckoo filters will say they're full and reject new adds. However, Redis will do the same thing with cuckoo filters that it does with bloom filters and add a second one. And then, of course, that increases the amount of time because you have multiple filters to check. You can use it by calling CF reserve. Set up a key and a capacity. Very easy to set up a cuckoo filter. CF add adds an item. CF delete deletes an item. And it's just key item, key item. It's a very simple interface. You call exists to say, is it in the item or not? Count will give you that count back if you want. Add NX is, I think, particularly interesting because add NX will add it if the count is 0, if it's not there. Add if it doesn't exist. But if it does exist, it won't increment it. And this could be useful because you don't want to use the counting aspect of it. But it's a little slower because it's got to check to see if it's there before it adds it. Whereas CF add just goes ahead and does the math and adds. It just goes and does it. So depending on your need, you may want to use one or the other. Here we are reserving a cuckoo filter with a capacity of 100. We're going to go ahead and add Thomas Edison. We get a 1 back. We're going to add George Westinghouse and get a 1 back. We're going to add Nikola Tesla, and we also get a 1 back. And we're going to add Thomas Edison again, and we're going to get a 1 back. It always returns 1 to say it's okay. If it's not okay, it will give an error. So at this point, Thomas Edison's been added twice, and so he should have a count of 2, whereas George and Nikola have been added once, and so they should each have a count of 1. So let's call CF count, and we see that indeed Edison does have a count of 2. If we delete Edison twice and count it again, you can see that Edison has a count of 0. We can check for existence of Tesla. That's going to return a 1. Tesla is in there, and he has a count greater than 0. Westinghouse, that's true as well. But if we call CF exists on Edison, he's been deleted out of existence, and so only has, so it's going to return a 0. He's no longer in the cuckoo filter. So it's your turn to play with the cuckoo filter. Set up a cuckoo filter with contain up to 100 email addresses. Check that your email's not there. Add some emails. Add some of them more than once. And then check your addresses. Check that the ones you've added are probably in a filter. Check for the ones you haven't added are definitely not in the filter. Go ahead and count one of the email addresses, delete some emails, and count them again so you can watch that count go down. And so go ahead and pause the video, and I'll be here when you get back. Cool. So hopefully that was a useful exercise in just kind of playing around with the cuckoo filter and see how you could use it for yourself in your own applications. Let's move on to count min sketch, which finds frequency. So what do we mean when we say frequency? Well, frequency is counting, but it's counting in a different way, right? When we were looking back at HyperLogLog, it would count the number of items in a set, the cardinality. And so we could use that for like YouTube videos where we could say how many unique people watched this video by adding the people to that set. With frequency, with count min sketch, instead we can have a set of videos and increment the number of times that video is in the set by the number of views it's had. And so there's a number associated with that item, that element in the set. And so here we've got our star's got 5, our square's got 4, our circle's got 6, and our triangle's got 3. And so these are numbers that are associated with, this is the number of times the circle is in this set is 6. But the cardinality of the set's still 4. Count min sketch is a fairly straightforward data structure to implement. To use it, you need to know a little bit of how it works internally. It's not very complicated, but it's still necessary to know it. It supports adding members. So like all of them, you have to be able to add stuff. You can count occurrences of the members, and you can union count min sketches together. However, you cannot get the members. You can't ask a count min sketch to say, tell me all your members. You can't delete members. You can't count the members. You can count the occurrences of a member, but you can't count the members itself. You can't get the cardinality. And you can't get intersections and differences. Internally, a count min sketch stores the hashing of whatever you add to it in multiple arrays. And the arrays have a particular width. And what you do is you take the text that you want to add and you run it through each of these hash functions. And that will give you a unique number. And then you divide that, you get the remainder of the width of this structure. And that remainder is used to select the index that you then increase the count of. And this table here is just full of zeros and other numbers, and the numbers go up over time. And in some ways, this is kind of like a hash table. Bloom filters have a similar structure internally. Occasionally, you'll have collisions. So like this 12 here, if we add something, maybe it matches up with that, and it's 13, even though it's not actually that particular string that generated that. And so these numbers can sometimes be higher than they're supposed to be, but they'll never be lower than they're supposed to be. When you go to get the count out of it, you just go through every hash that matches your string, and you just get the minimum count in this table. So that's why it's called a count min sketch. You're counting the minimum count in this sketch. Because you're just going through a series of hash functions, adding new items and getting occurrences is a time constant operation. And it also means you can merge them, where you can take multiples of these structures and just add them together. However, this will only work if they have exactly the same depth and width. And of course, doing that is going to be equal to the number of things you want to merge. But it's a fairly straightforward operation. There are two ways that you can initialize and create a count min sketch. The other ones have had like CF reserve and BF reserve. This has a init by dim, by the dimensionality of it, and a init by probability. The dimensionality says I want one that's this wide and I want one that's this deep, just like the table we saw. And so that's one of the reasons we went into explaining the table, is so that you can understand when you're creating these what that width and what that depth mean. You can also init by probability, and again you pass in a key. And the error is the overall error count in the entire hash table. How wrong is it? The probability is how likely it is any particular one is wrong. And you can take these two values and compute how wide and how deep it would need to be to get those probabilities. And so if you care about probability, you can do it this way instead. It's got an increment by, which just increases the count. You give it an item and an amount, and an item and an amount. And then if you want to query that count, you can say, just give it to me and a list of items. And if you want to merge, merge is kind of interesting because you've got this destination key, and you've got a couple of source keys and number of source keys, but it needs to know the number of keys you're going to pass it before you do that. So you've got the destination key, the number of keys you want to merge, and then each key name. And so that's a little different. It's a pattern you see in other parts of Redis. Why would you use count min sketch? You use it to count a set of big things with a small footprint, just like everything else, right? Views for each video on a video hosting service, for example. This is similar to the problem of tracking users on videos, right? So you've got the set, this video has a HyperLogLog for all the users, and so you add all the users and you get a count of the number of users that have seen it, and you don't get any dupes. In this case, you could have a set of videos, and then you could increment the count for every single time it was viewed. And so it lets you treat it as a set. So it solves a similar but not exactly the same problem. It's sort of a 90 degrees off. And it doesn't do that uniqueness when you're adding those counts. You're just adding unique numbers. So they solve slightly different problems, but they are certainly related. And of course, this applies to upvotes, visitors to each of the URLs on your site. You could have a count min sketch that the set is all the URLs on your site and how many times they're each visited. You could do search terms on a search engine for each user. Each. That's kind of the theme here, as opposed to unique with the HyperLogLog. Set up a count. Here's init by dim. You pass in. We're going to do views by country of video. And we want a width of 1,000, depth of 5. Or we could take a probability view and say, I want the total error to be 1% or less, and I want the probability of an inflated count to be 0.1%. And so you can create these either way. To increment them, we're going to call the incr by, INCR for increment by. I like to say incr b because I think that's kind of funny. And we're going to pass in views county, and then we're going to say the United Kingdom has added 3 views for this, this video. Yeah, here we are going to do another incr b. For countries, again, this time we're adding 1 for the United States and 2 for the United Kingdom. Now you notice in both of these cases we were returning a value here. 3 was how many that value is. And here we're returning the updated value. The United States was 1. The United Kingdom is 5 now because 3 plus 2 is 5. And here we can then call query, count min sketch query, and we can pass in countries that we want to query. And we're going to do the US, the United Kingdom, and Canada. Now we haven't added Canada before, but we're going to query it. And we get 1, 5, and 0 because Canada has never been added to the count min sketch. So it's your turn to play with a count min sketch. So let's. How about we set up a sketch to count the colors of objects in the room you're in. So I'm looking around my office right here. I see some green things. I see some red things. You can see the background of my office. There's a lot of brown in my office. There's a bunch of colors, and so I'm going to create a sketch, and I'll start adding room colors, and how many items of those colors I see. Increase the counts of the colors based on the objects in my room. Query a color that I've added, right? That you've added. Does it return the amount? It will. Query a color that you haven't added. What do you expect that will return? Query all the colors in the rainbow with one big statement. Get red, orange, yellow, green, blue, and purple, and see a little graph of sort of the rainbowness of your room. And if you want a fun bonus activity, set up a sketch and count the colors in another room, and then merge those sketches together. And that should take you about 5 minutes, maybe 10-ish. So go ahead and take a stab at that, and I'll be right here. Excellent. So hopefully that was edifying. Did you do the bonus activity? If you didn't have time, that's fine. You can go ahead and try that out later. There's actually some other commands here. Here's the merge that I sort of suggested you might want to try. Here we're initializing by dimensions, a couple of views by state in the United States. So we got views for Ohio, and we got some county by county additions. So we got Franklin County, which is where Columbus is at. That's where I'm at. Cuyahoga County, which is way up was where Cleveland's at. And little old Auglaize County has had one view for this video. Auglaize is actually home to the thriving metropolis of Wapakoneta, and is where Neil Armstrong is from. So there's a museum there for him. It's kind of fun to visit. It's a little good one-day sort of trip kind of thing, if you happen to be in the area. So we add these, and then we go ahead and create one for Florida. And same size. They have to be the same size, same width, same depth. And we're going to go ahead and add 63 for Dade County, 27 for Orange County, 12 for Polk County. And then we're going to merge. And here you see we're going to say reviews total. Number of sources is the number of source keys that we want to merge together. So Ohio and Florida are our two, so we put in 2. And then we put in the 2 source keys. And then I'll merge those together. And then you can use that as another min sketch. And you can, of course, then take that min sketch, count min sketch, and merge it with others, and do all kinds of crazy stuff. Okay, so last but certainly not least is ranking with top K. So revealing rank with top K, let's dive into a little bit of what we mean by rank. So count min sketch has numbers associated with all these bars, right? Ranking is putting them in order based on those numbers. And top K does that in kind of a unique way. But I mean, ranking is sort of an idea. It shouldn't be that terribly foreign, where you just want to find the top number of things. Top K is, it confused me when I first heard it. I'm like, top K, is that like special K? No, it's not like special K at all. It's top K is the top N things. That would have been how I would have said that before I learned about top K. And so if you want to find out the top 5, titles most likely to get killed by clickbait filters, then you could use a top K structure to do that, and that would find the top 5. And so it's a set just like before, but it's a ranked set. So top K supports adding members, of course, checking membership, counting occurrences of members, just like count min sketch, and getting members, but only if they're members of the top K. So if they're in the top 5 whatevers, then you can do that. But if they're not, you can't ask that question. If you check the membership on something that's not in the top K, it will say it's not in the top K, so it's not in the list. It's in the set, but it's not in the top K, so it doesn't matter. And same thing for counting them. You can go and get the count of a particular member in top K, and you can get a count. But if it's not in the top K, you can't. It doesn't support deleting members. You can't count the members themselves. You can't get the cardinality. And you can't do unions, intersections, or differences. About top K. Well, we actually have a good blog post on this on our website, which I encourage you to go check out. He takes all the words in War and Peace and then counts them. And basically what he found in his benchmark was that it's 4 times faster than a sorted set. You could use a sorted set to do this sort of stuff. And it would be deterministic. It would be guaranteed to be right. This is 99.9% right. 4 times faster and uses about 1/100th of the memory. And so you can see how a top K could be a very powerful structure. Top K will report deflated counts. In other words, counts that are lower than they should be, but they'll never report ones that are higher than they should be. And top K stores has this hash 2-dimensional width and depth structure, very similar to count min sketch. But in addition to storing a count there, it also stores a hash, a fingerprint of the particular string or data that resulted in that field being filled, or that cell being filled. And to decrement them, because they can be decremented, there's a small chance of that happening. And that chance varies depending on what the count is. And the net result is that you end up with what they call elephant flows and mice flows, or mouse flows. Elephant flows are big and heavy, and they have large numbers, and the odds of it going down by one decreases the bigger and bigger and bigger it gets. Whereas if something's small, the odds of it being removed is fairly high. And so this forces it to keep the heavier things. And so this structure that we looked back here in the previous slide is called a heavy keeper, because it keeps the heavy things and throws out the little things. It's not that the heavy things can't be kicked out. It just needs a bigger thing to kick it out. A mouse might be able to nip at it a little bit, but it's unlikely. But if enough mice of the same type collide with it, then they're not mice anymore. It's an elephant, and it starts whittling away at that and can replace it. But the top ones are always preserved because it's a heavy keeper. Top K commands. Using Top K is not terribly difficult. It's got the reserve, and this is the one where the width and the depth, again, the implementation kind of matters because you specify things that the implementation uses when you reserve it. And so you're going to Top K reserve with a key. You're going to give it a K. That would be the number of items you want to rank. You give it a width and a depth, and you give it a decay rate. Now, it's not actually really the rate of decay. It's the factor that goes into whether how rapidly things will decay. And so if this number is larger or smaller, that will affect whether elephants get eroded faster or slower, and whether mice can do that or not. And so that decay rate affects that. I found that I need to play with it to find the right level for what I'm doing. And the width and your depth and that decay rate is going to depend on the nature of your data, as well as how much probability or uncertainty you're willing to take on. Adding things is easy, as always. Topk.add, key, item, and then you pass an n number of items. You can also increment by. Topk add is just add one to the thing. Increby is, you give it an item in an increment and say, well, no, increase this by 5 or 10 or 50 or 1,000, whatever you want to increase it by. Query will let you query whether something is in the top K or not. It will return 1, it is in the top K, or 0, it is not in the top K. Top K list gives you the top K items. And then top K counts will let you check the count of an item if it's in the top K. So what might you use Top K for? I think you could use it in a kind of fun way to find commonly used search terms for predictive text. Showing top or trending content based on user interaction. You can use it for leaderboards for sports or video games. This is a really obvious application. Show me the top 10 high scores for an MMORPG or something like that. And a common use for this is analyzing IP traffic as it comes to servers. Show me the top 5 largest sources of traffic for my server, and you can use that to analyze threat vectors. So we're getting a lot of traffic from this, this server in this place here. I wonder what's going on there. Maybe we should look at that server. And it looks like it's trying to, do a DDoS or something like that. And so then you can shut it down. Here is setting up a top K. We call topk.reserve. Here we're going to do some various pharmaceuticals. We're going to keep track of the top 3 most, let's say, prescribed pharmaceuticals. Give it a width of 100, a depth of 5, a decay of 0.9. If you make that number bigger, decay is less likely. If you make that number lower, decay is more likely. And so we create a top K. Now we're going to add some drugs to our top K. Topk.add drugs, pass in acetaminophen, lisinopril, and azithromycin. And these all should have a count of 1 now. And you'll notice that it returns 3 nils. And I'm not going to tell you what those 3 nils are for yet, because they're actually there for kind of an interesting reason. And it'll be more obvious as we move through the exercise here. Here we're going to call top k increby, and we're going to increment acetaminophen by 4 and lisinopril by 3. And again, we've modified two things. We should now have acetaminophen should have a value of 5, lisinopril should have a value of 4, and azithromycin should have a value of 1. And but we modified two things, and we got 2 nils back. Let's add a new contender, hydrochlorothiazide, that wonderful, wonderful blood pressure controlling medicine. We give that an increment of amount of 10. Now, it doesn't exist yet, but we're adding it and we're incrementing it. So we're just saying hydrochlorothiazide 10. And this time it returned something. It returned azithromycin. See, what happens is it actually returns the thing that it displaces. We're doing a top 3. And so at the first statement up here, our top 3 were the 3 that we added. In here, we didn't add any additional drugs, and so there were still only 3 in the entire set, and so they were all in the top 3. However, hydrochlorothiazide, I really should have picked easier drug names to say, shouldn't I have, is all of a sudden in the number 10 position. So that puts it in the, it's got 10, so it's in the number 1 position. And so something has to be bumped out of the top 3, and azithromycin is the one that was bumped out. And you can confirm this by doing a query. If we ask, is acetaminophen, lisinopril, and azithromycin in there, you'll get a 1, a 1, and a 0 back. And that 0 right there means that azithromycin is not in the top K, not in the top 3. If we do a top K.list, we can get a list of the things that are in the top K. And we see it's lisinopril, acetaminophen, hydrochlorothiazide. And if we do a top K.count for the things that are in our top 3, we can actually see the numbers. And we can see that hydrochlorothiazide has the 10, the 5, and the 4, and we're getting them back in a descending order, or in an ascending order. So the most highly ranked one is last. Now, I've found that if you use really small numbers, sometimes these orders can get a little messed up, but with larger numbers, it's more consistent. So if you don't see them not quite lining up the way you do in the exercise, don't worry, it's fine. You can still look at the count here and get that sense of top K-ness. So it's your turn to do the exercise. This is the last exercise we have. Set up a top K to rank the 3 best flavors of ice cream. In my mind, that's pistachio, black cherry, and butter pecan. Your mileage may vary. Name an ice cream, give it a width of 100, a depth of 5, a decay of 0.9, and a K of 3. Add 3 flavors that you like. Set the counts wherever you want. But don't add your favorite. Then add your favorite and make sure the number for the favorite using either increby is larger than all the other ones, maybe even combined. It is your favorite after all. And after you add your favorite, you should have a flavor returned. Which flavor was it? And why was that returned? And why wasn't a different one returned? Why was a flavor returned at all? Query the top K for your favorite flavor and for the flavor that was returned. And see what you get. And list the top K flavors. And that should give you a nice, good feeling for how top K works. I'll sit here and wait for about 5, maybe 10 minutes for you to work through the exercise. And yeah. All right, so how'd the exercise go? What was your favorite flavor of ice cream? What happened when you did the top K for your favorite flavor and the flavor that was returned? What should have happened is that your favorite flavor should have been in there, and your flavor that was returned should have been removed and would not be in there. And so hopefully that's what you saw. And hopefully this was a useful exercise to help you get your head around top K a little bit. So that's pretty much all I've got. We've gone through 5 probabilistic data structures and some talking, some speaking, some articulating about what probabilistic data structures are. And so probabilistic data structure are these data structures that have inaccuracy in exchange for better performance and space characteristics. A HyperLogLog is a thing that can count unique items. to a ridiculous level, maximum of 12 kilobytes of space, can count all the atoms in the universe. Super, super cool. Bloom and Cuckoo filters allow you to check for membership. They can tell you whether something is definitely not in them or whether it's probably in them with a degree of error that you can, with a Bloom filter you can control. Count min sketch lets you find the frequency of items in a set, so you can, well, basically, it's sort of like a bar chart. And so that can be very useful if you've got a set of things that you want to keep counters on, but they're really big and you want a nice tight structure as opposed to using like a sorted set or something like that. And last but not least, we have top K, which allows you to maintain a set of the top K most items that match a particular count that are of the greatest count in the set, and sort of discards the rest. And that's what top K does. It's a very powerful and complex data structure. If you ever have the chance to go deep inside of how it's implemented, it's quite fascinating, and it's a remarkably effective data structure. So those are the 5 that we've talked about. Hopefully that's answered a lot of your questions. If not, I'll be in a Q&A session later this day, and you can go and ask me questions about these data structures. And so, yeah, that's all I got. So thanks a lot, and enjoy the rest of your conference.